First thing first, as I promised, here are some more plans for our midterm 2. So I posted this announcement on BrainLearn. You should also be able to check it on your own whatever device you like. But basically what we have started from what's the coverage, right? So we're gonna cover the lecture 11, which discuss the physical meaning of entropy and link entropy with probability all the way until our next Monday's lecture. So hopefully I'll be able to finish conventional entropy as well as the third law of thermodynamics. But we'll see, right? Whatever I finish next Monday, that's going to be our end of our coverage for midterm 2. All right. When and where? So these are pretty straightforward. Your midterm exam is scheduled next Friday. So in midterm 1, if your UID ends with an even number, you stay in this room. If your UID ends with an odd number, you go to the other room, right? So that's the last midterm. For this midterm, if your UID ends with an even number, your midterm will happen at Dot Hall. And if your UID ends with an odd number, your midterm exam will be here. Now your TA will be with you in this room. I'll meet you in Dot Hall to administrate the exam. Exam is likewise 15 minutes in class time. What to expect in the exam? Now, again, our exam is open book, open note. You can use whatever lecture note you want, periodic table, equation sheet, calculator, whatsoever. So as long as it's not it's not an electronic device that's connected to internet, you'll feel free to use it. Also, during the exam, if you're like, oh, I forgot what the gas constant is, or like, I don't know what does 1 Pascal transfer to 1 bar, right? So these kind of constants, we'll try to provide it to you, but if I forgot and you don't have that in hand, just ask your TA or me, because we'll put it on the board. We don't want those like small information to obstruct you from finishing the exam. Then structure of the midterm. So based on our votes for midterm 1, I think 53% of you voted for like exam difficulty is okay, but too long, you don't have time to check your answer. So I took 1 short problem away. So now your exam will be 10 true and false problem, and then 4 short answer problem, each worth 25 points, and then 1 comprehensive problem with multiple parts. All right, so the structure will be similar, just 1 less short answer problem. And then study suggestions, these are pretty much stays the same as I told you last time, right? So whatever problems in the chapter end problem, I use those chapter end problem to survey for what to put on the exam. So mastering the chapter end problem will be a very good preparation, and also your discussion worksheet. And also, I posted a short survey called Midterm 2 Buffer Lecture. Just select like 3 topics, and those are the topics you feel like you're most confused about and you want me to spend more time. So we'll go over those topics on our next Wednesday's Buffer Lecture. But keep in mind, we only have 15 minutes. So if you select everything, I have to make a choice, right? So please select only up to 3 of those topics. I'll try my best to cover as much as possible. And then also, like, I highly recommend you come up with your own 1-page equation sheet so that you know where to refer to. And also, as we mentioned in our last lecture, whenever you put down the equation, make sure you also put down what are the conditions of that equation. What are the terms in that equation mean, so that you know when and where to use those equations. All right. And at the very end, we offer partial credit. So it's important for you to set up the calculation, then getting the final answer right. So setting up the calculation worth like 50 to 70% of your grade, and getting the numeric answer is only the very last part. And yeah, and next week you won't have any discussion worksheet. Your TA will tell you more information regarding what we're gonna do for the last 2 discussion worksheets. And I have also posted my previous midterm 2 exam on BrainLearn under the module called midterm 2 But keep in mind, the coverage is different, the pace is different, and it's from previous quarter, right? I don't have an answer key for that exam, but I do have a walkthrough for that previous midterm 2 exam that's on YouTube, that's on our YouTube channel. Just click into the 23-4 playlist and you should be able to find that. All right, any questions before we go on? Nope, we're happy? Okay, sounds good. All right, so back to where we left over. So in our last lecture, we started by talking about standard state, standard enthalpy of reaction, and then standard enthalpy of formation. Right, so this is the typical thermodynamic table. This one is from your appendix. I will probably print it out, this appendix table for you for the midterm exam. Otherwise, I'll give you the number. But nevertheless, so these are the thermodynamic table that we used in our last lecture to solve for reaction enthalpy. Right, so if you remember, in our last lecture, we went over, say, the delta H of the reaction goes to the sum of my stoichiometric number I times the delta H naught of the heat of formation of each species. Right? So using this table is one thing. The other thing to notice is for a compound that is already in its standard form, we'll notice that the delta H will be 0. So if we look at carbon in its graphite form, now the carbon solid in its graphite form is already its standard state of element carbon. So the delta H formation of carbon, standard enthalpy of formation of element carbon will be 0. Or alternatively, we can ask you the other question. It's like, what is the standard state for, say, Br2? Want to take a guess? Right, so this one, as we can see, since Br2 liquid has delta H formation equals to 0, then that's our standard state for element bromine. Right, so 2 ways to use the thermodynamic table. So in today's lecture, we'll go over 2 topics. First topic is focusing on this part, right? How did scientists measure the standard heat of formation of a species that is not in its fundamental elementary form? All right, so we'll go over steps scientists take to set up the experiment. How do we perform the experiment? What kind of calculations are involved in the process of getting these numbers? All right, knowing how to use it is one thing. Knowing where these numbers come from is a separate question. That's our goal for today. Secondly, we'll also talk about the relationship of this CP0 PM. So this one is the isobaric molar heat capacity, or the standard isobaric molar heat capacity. We'll use that to build a link for the temperature dependence of our enthalpy. All right, so 2 goals of today. The first one will take like 45 minutes. The last one will take 5 minutes, but it's fine. Let's get going on lecture 10. All right, so measurement of the heat of formation. So I'm gonna copy these on the board and also give you a little bit more information, and we can do it together. So think about what is the goal here. We're trying to measure, or we're trying to set up a way so we can measure the standard heat of formation of something that we want to know, right? So in this case, let's imagine we have a reaction, like say the formation of HCl. Right. So one of the obvious things that we need to know is for these 2 elementaries, what we know is their standard heat of formation equals to 0. But the problem here is all the gases, their standard states are ideal. So we're trying to find the ideal gas, or the ideal HCl gas, ideal hydrogen gas, ideal chlorine gas, and what's the delta H for these reactions between ideal gases. Now that's something we cannot directly measure, right? Because technically speaking, in the lab, we do not have ideal gases, we have real gases. So what do? We have several steps. The first step is we want to transfer something we know. Like for example, in our starting material, we know these are ideal gases. We need to transfer them into real gases so we can have them undergo mixing, undergo reactions with each other. So the first thing is we want to make them from real gas. Let's say H2 and Cl2 into ideal gas. All right. And in our original condition, what do we have here? These are the standard state at 298 Kelvin, or some random temperature, let's say 298 Kelvin. Now what we have is real gas at 1 bar, 298 Kelvin, and after this transformation, we'll get it to hypothetical ideal gas at 1 bar, 298 Kelvin, right, and separated with each other. We want them to react with each other, so the next step is mixing them. And thirdly, I think this arrow bar goes the other way around. We're trying to transfer their standard state into their real gas, 298 Kelvin and 1 bar. Sorry for the misunderstanding. So we started from the hypothetical ideal, that's the standard state for H2 and Cl2. And we want to make them real gas. All right, so next step is mixing of gases. This one we won't talk too much in this lecture. It's just knowing that we have a way to measure the delta H for mixing of these reactants. Third step. Remember, these are at standard state, or 1 bar and 298 Kelvin. But in our reaction, we're not necessarily performing the reaction at 1 bar and 298 Kelvin, right? For example, in calorimetry, we may want to perform the reaction at much higher pressure, like 80 bar. So we need a way to translate this temperature and pressure into the actual reaction temperature. So our third one is called calculate changes of enthalpy with respect to temperature and pressure. So do we know how to do that calculation? Right, so remember, in thermodynamic relations, we have several relationships. First of all, we have the partial differential of H over P at constant T. So that's called the pressure dependence of enthalpy equals to negative PV alpha plus V. Or you can have isobaric heat capacity, H over dP, at constant P equals to Cp. Right, so in order for us to calculate how enthalpy is going to change with respect to temperature and pressure, we can of course use like isothermal pressure change followed by isobaric temperature change, or vice versa. But nevertheless, what we can have is delta H. We take the integral from T1 to T2 Cp dt plus P1 to P2 V minus TV alpha dP. Right, and note it here, like knowing the equation of state, we'll be able to solve for V and alpha as a function of P. right? So we have ways to solve that integral. So that's the third step. Fourth step. So this is the one we will talk about later, which is calorimetry. Basically, calorimetry tells us the reaction enthalpy. The actual reaction enthalpy for the real gas H2 plus real gas Cl2 go to 2HCl gas at certain temperature and pressure, depending on the setup of the calorimetry. And then, what about the next? Now our H2 and Cl2, we first started from ideal H2Cl2. We translate that into real H2 and Cl2. We mix the real H2 and Cl2, my reactant, in a chamber. We have them react using my calorimeter. And now we have my HCl, which is my product, as a real gas at certain temperature and pressure for my calorimetry to take place. So let me put this one. This one is say, originally we're at 1 bar and 298. Calorimetry we can add like T prime and P prime, right? So number 5 is obviously we want to translate this back to the standard state, right? Which is 1 bar and 298 Kelvin. So this is change P back to 1 bar and 298 Kelvin. And now we have HCl gas real at 1 bar and 298 Kelvin. So far so good? About the last one. We'll transfer that real gas back to ideal gas to finish our original equation. All right. So I hope that gives you an idea about what people are doing when we're setting up the way to calculate for the heat of formation. The 6 different steps. Now, let's focus on number 4 here, right? So think about it. 1 and 6 are effectively the same. 2, we're not going to worry about. It's just knowing we have a way to measure number 2. 3 and 5 are the same with each other, and we have a way to calculate 3 and 5. Now, today we'll first talk about number 4, which is what is calorimetry, right? How do we use calorimetry to measure the reaction heat? The second goal, later on, we'll talk about how to translate real gas versus ideal gas and vice versa. So the first goal here is number 4, and the second goal here is number 1 and 6. So I'm going to go back to my iPad. Yeah, and basically on my iPad, you have the same thing. I'm just writing it down again with a little bit more illustration. Okay, so calorimetry. So this is the experiment physical chemists set up so that we can measure the 4th step, which is how does the reaction takes place, or how much heat is being released or absorbed when a chemical reaction is taking place. Now, inside a calorimeter, we have several things. First of all, this entire calorimeter typically is covered by a thermally insulated wall, right? So if we're considering everything inside the gray box, that's thermally isolated from the rest of the universe, right? And also these walls are solid. So if we consider the overall calorimeter, now the total internal energy must be 0. It's not exchanging heat, it's not doing work with the surrounding. And then in here, we have several things. So inside here, this is what we call a reaction chamber. Typically, if we're considering a combustion reaction, this reaction chamber will be pre-filled with oxygen gas. And then later on, we put a sample pellet of whatever starting material we want it to be. we have a ignition wire to initiate the reaction, and that's what the reaction chamber is doing, right? And then surrounding the reaction chamber, we have a huge water bath. Now this water bath, in order to measure how temperature change, we obviously have a thermometer around it. We also have a stirrer around that water, in that water bath, to make sure the temperature is uniform within the water bath. And then you also have electrical heater so that we can manipulate like which temperature I want this water bath to be. So a little bit of the notation, what we call in that constant volume bomb, we have reactant, we have product. So for using our example here, our reactant will be H2 and Cl2. My product will be HCl. And we call our water bath just big K. So that's a setup for our calorimeter. All right. And in this setup, we know that delta U total equals 0. So whatever amount of energy that's being released by the reaction, it's going to be absorbed by the water bath. And whatever energy that's so basically they'll have the same number, just different sign when we're talking about internal energy, because total delta U of the entire calorimeter equals to 0. All right. So then the question becomes quite straightforward, right? So we have our initial state. That being our reactant. Again, we annotate that with R plus our water bath. Or we annotate it with K. At certain temperature, we can assume that's 298 Kelvin. It doesn't need to be 298, it can be other temperature as well. And then upon the chemical reaction, we get to our final state, which is product P plus water bath K. And now the temperature will change. So our new temperature will be 298 Kelvin plus delta T. So that delta T will be positive if it's ectothermic, if the reaction releases heat, be negative if the reaction absorbs heat or an endothermic process. And what do we want? We want to get the delta U between your delta. We want the state. Let's see one more thing. It's my product plus water bath. It's at 298 Kelvin. Right, so after the reaction, we eventually want the water bath to cool down, or we reheat up the water bath, and so that's back to the original temperature of 298 Kelvin. So that by looking at the difference between your initial state and the desired state, we know that how much heat is being generated or absorbed during the reaction. So the delta U of the process then becomes quite straightforward, right? So we have the delta U of this reaction at 298 Kelvin equals to negative of K plus P delta T. Now this K plus P, that tells you that's the heat capacity of my entire bomb or the calorimeter, including the water bath and the reaction chamber including my product, right? So we have a way to measure this heat capacity of my water bath plus the product. Delta T is the amount of energy, amount of temperature changed. So heat capacity times delta T gives you your change of internal energy in here. so this part is pretty much just going to be a very straightforward plug-in number type of question if we ever ask you. So for example, this is the kind of question you might see in your textbook. Assuming we have combustion of 2.016 gram of solid glucose at 25 degrees Celsius in an adiabatic bomb calorimeter, with heat capacity given, and we tells you the temperature rise of 3.282 degrees Celsius, and ask you to find the delta C U298 dot. I really don't like this notation, but this one is just say that's the delta U 298 for 1 mole of glucose. All right. So how do we set up this calculation? This one is quite straightforward, right? So what we have delta U 298 equals to negative C K plus P times delta T. And do we know what they are? Right, we know. So our heat capacity of my calorimeter is given to be 9550. My delta T is given to be 3.282. So plug in the number, you'll get the delta U for the combustion of 2.016 gram of solid glucose, and translate that into number of 1 mole of glucose, you get your final answer. So this part is very much just plugging numbers. All right, so that's a setup of calorimetry. And what's the logic behind calorimetry? How do we use calorimetry to measure the change of internal energy? And one last step is now we have the change of internal energy. Remember, what do we want? We want the change of the heat of the reaction, or the delta H, the change of enthalpy of the reaction. So I need to take one more step to translate the delta U that we measured into delta H. Right, so what do we know? We have the definition of enthalpy. So H is by definition equals to U plus PV. At standard pressure or standard condition, we know that our pressure is always kept at 1 bar. So think about this one. What do we have? Why do we have this expression here? Again, it's always safe to take differential on both ends. So my dH is always equals to du plus dPV, or dH is always equal to du plus pdV plus VdP. Right, so these are just always going to be true no matter what. And then, using constant pressure, we know that dP equals to 0. Right, and we take the integration on both ends. We have dH equals to du plus pdV. Now, pressure is a constant, so that's why we can take it out. And that's how we get delta H naught equals to delta U naught plus P delta V naught. Right, so that naught denotes for standard state. So one common mistake in our class is make sure you know where to get it. Like, for example, in here, when reading the textbook, it's very straightforward to say, oh, yeah, that looks fine, right? But if in a true and false, we remove that dot and tell you, like, is this one true? Like, it's not. If the pressure is not constant, it's not true. Yes? Which one? Oh, yes. Thank you. All right. So how do we apply that into translating delta U and delta G in our condition? Right, so the only difference between delta H and delta U is this term, the P delta V naught. So this delta V naught, if you think about it, that's the standard volume, that's the volume change of the substance we care about at standard state. So typically, my delta V naught is negligible for liquid and solid, right? So for anything that's not gas, the delta V naught is going to be negligible. And this is quite straightforward to think about because depending on the change of your temperature or your at constant pressure, I mean, changing your temperature, your volume of liquid and gas will change, but that change is very, very, very small. Yes.
Liquid and gas?
Solid. Gas will be different, and we will talk about it. And what about gas? Right, so that's a very good question. Like, what about gas? What do we know about the standard state of gas? And the standard state of gas is ideal. So what do we know? We have PV equals to nRT, right? Or the other way to put it is if we think about V naught at constant pressure, I mean, R is a constant. R is a constant. What do we have? V naught equals to nRT divided by P naught. All right. Or the other way to put it is we have delta H naught equals to delta U naught plus delta NG RT. I'll explain it. So these are the things over P naught times P naught. Okay, let me not skip any steps. And my P naught and P naught cancel out. So we have delta H naught equals to delta U naught plus delta N times RT. Right? So when we're talking about delta H naught, delta U naught, typically we're talking about a defined temperature. So temperature is also not changing. We're only talking about the change of number of moles that's related to the difference between your internal energy and enthalpy. Now in here, remember, delta V naught is negligible for liquid and solid. So we really only care about how much number of mole of gases are involved in a chemical reaction. Or the more general expression of this equation that becomes delta H naught equals to delta U naught plus delta NG RT. And this delta NG tells you it's the number of mole of gas molecules. Or change of. All right. Now let's look at one example together to see like how to use it. For example, let's imagine we have this molecule CF2Cl, CF2Cl. And this one we tell you, you can, or you by serving the thermodynamic table, you find out the delta H standard heat of formation of this molecule in 298 degrees, 298 Kelvin is equals to negative 890.4 kilojoule per mole. Can you find the delta U formation of this molecule? Right, so how do we approach this problem? First of all, write down the equation for the formation of this molecule from its elementary form. And this one we have, well, 2 carbon atoms. Well, we have 4 fluorine. The elemental form is F2. It's a gas. And if you're in doubt whether its elementary form is gas or liquid, check the thermodynamic table. And Cl2, which is a gas. And all these elementary form go to our final product, CF2Cl, CF2Cl, which is also a gas. Right, so for this entire process, in our reactants, we have 3 gas molecules. And in our final product, we only have 1 gas molecule. Or the other way to put it is our delta Ng equals to negative 2. And you can plug in the number to get our final result there. All right, so in this section, we started by looking at what do we need in order to get the heat of formation of a random molecule. And then by working out, we see like, okay, we need an experiment that's called calorimetry that measures what is the reaction heat for some kind of reaction to give you the product. And what about more complicated reactions, right? So the HCl formation is quite straightforward. What if we have more complicated multi-step reactions? So in order to address multi-step reactions as an atom, we have the Hess law. This one is super straightforward. So I'm just gonna do one example with you and you'll get the gesture. And there's one practice problem, you can do it yourself. So in Hess law, what it's saying is that the overall enthalpy change of a reaction is equal to the sum of the enthalpy change for the individual steps in the reaction. All right, so we're talking about a multi-step reaction. Like you can just do the overall sum of every individual step to get the final overall reaction enthalpy. So if we use the Haber process as an example, it's a multi-step reaction. It's basically 3 hydrogen. The overall reaction for the Haber reaction is 3 hydrogen reacting with 1 nitrogen to give you 2 NH3. But in the actual mechanism for the Haber reaction, we can break it down into 2 different steps. The first step involving my hydrogen and nitrogen, which are my reactants, to form a molecule of N2H4. And we call it an intermediate because the generated N2H4 will then be used up in the next step. And then the next step react with another molecule of H2 to form our final product. All right, so for my first reaction, we have delta H naught 1 equals to delta H naught of my N2H4 minus my reactant, delta H naught, 2 delta H naught of my H2 plus delta H naught of my N2. And this process is actually an endothermic reaction equals to 95.4 kilojoule per mole. You can check that up by looking at the thermodynamic table. The second step, delta H naught 2, that equals to, again, product minus reactant. So 2 delta H naught NH3 minus delta H naught of N2H4 plus delta H naught of H2. And this one is an exothermic reaction, right? So the overall reaction is the sum of these 2 steps. Or if we put it in an energy diagram profile, it's going to be more straightforward to see. So in this case, what is our first step? We started from our 2H2 plus N2, so that's our first step. It's endothermic, so we're absorbing heat. The next step is from my reactive intermediate all the way go to product. That's my second step. And my overall reaction is the one like this. All right. So that in this part, when we say Hess law, it's basically simplified to say like whenever you have multi-step reactions, you can always build your overall reaction by looking at each elementary step that we can calculate their reaction energy. So these are one more practice problem to see if you can calculate the standard enthalpy of hydrogenation of liquid benzene. So I'll leave it for you to practice. You'll see that in our annotated note you can check your answer with. All right, next topic. Now we're here. We're ready to talk about the difference between your real gas and the ideal gas, and how to calculate the delta H for this process. So I'm going to keep this here just for your reference, but we'll do the we'll solve it on the board together. Right. So in here, let's think about the process. What do we want? We want to know, now we have H of ideal gas, and we want to know that difference between H of real gas. All right. And why do we care? Again, the standard state of my gas is ideal, so we want a way to translate or to at least calculate what is the difference between a real gas and an ideal gas. So the way to think about it, the actual logic behind these is thinking about in what condition my real gas and ideal gas are effectively the same with each other. So what is an ideal gas? An ideal gas is in which there's no intermolecular interactions between my gas molecules, right? So when my pressure is approaching 0, my gas will behave ideally. So that goes back all the way back to chapter 1 when we talk about the Charles experiment. So with that in hand, we set up our calculation to say like, hey, so now we started from real gas at P naught, which is 1 bar. Let's just reduce the pressure so that my pressure is at 0. You can't actually get it to 0, but let's say approaching 0, it's almost 0. And when my pressure is at 0, we have our part B, which basically we can say, hey, all my intermolecular interactions are eliminated. My real gas and ideal gas are the same when my pressure is approaching 0. And then we have ideal gas at 0 bar. We're ready to isothermally increase the pressure back from 0 to 1 bar, right? So what are the delta H for these processes? So the overall reaction equals to H ideal, that's our final state, at T and P naught, which is 1 bar, minus H real at T and P naught. Again, final minus initial. And that equals to our path add up to be together. Again, we can do that because my enthalpy is a path independent state function. It doesn't matter which path we take, right? So that's the path we built. So in here, what is my delta HA? What do we know here? So in here, for my first process, this one is a isothermal pressure decrease. To 0 bar. Do we have a way to solve for an isothermal pressure change? It's on the board. Anyone want to take a guess? Right here? Right. That's the pressure dependence of enthalpy. That tells us how does my enthalpy change with respect to pressure at constant T, which is exactly what we're looking for. So that gives us my delta HA equals to the integral. Now my initial state is P naught, my final state is 0. My negative TB alpha plus B dP. Again, with the equation of state, you have an expression of alpha. You can express V as a function of P, and you can solve that integral. What about my B? So as we were saying, when pressure is approaching 0, there's effectively no intermolecular interactions between my gas molecules. So my delta HB is effectively 0, right? Because looking at the physical nature of a real gas at 0 pressure, that's the same as an ideal gas. There's no interaction between your gas molecules. So this one just goes to 0. And what about C? C, there are two different ways you can solve for it. Obviously, we can use this again, because again, it's an isothermal increase of pressure for an ideal gas, right? You can definitely use this again, or more straightforwardly, since this is ideal gas, we know that the dH over dt equals to Cp, which is a function of T for ideal gases. Or for a constant temperature process, my delta Hc equals to 0. So one nice practice you can try is using the PV equals nRT and the definition of alpha and that equation to solve for delta H, and we'll see we get 0. All right. So in this part, what we end up getting is that the overall delta H just equals to this integral. And depending on what the equation of state is, we have a way to solve for this integration here. And then in addition, by just knowing the definition of alpha, we can simplify just one more step. So in here, we know that alpha equals to 1 over V times dV over dt at constant Pn. That's given in the definition of alpha. We can simplify this one by writing alpha in here, because volume cancels out in that expression. Okay, any questions? All right, next up. This part is going to be super quick because this part is really just a quick note to see like what is the temperature dependence of reaction heat. So far in this entire section, we were talking about how to get the heat of formation at a certain temperature and 1 bar, or the standard heat of formation. Now let's think about what about the temperature is different, right? What about we have temperature at 298 Kelvin versus temperature at 1000 Kelvin? How does the reaction heat change? So in this case, what we have, so this is what we derived before. So this is the total reaction, heat of reaction. That equals to the sum of your stoichiometric coefficient times the heat of formation of different species. And then in this case, if we divide both sides by dt, now thinking about the change of temperature. And what do we have? On the left-hand side, we have dH naught over dt. On the right-hand side, the stoichiometric coefficient is not dependent on temperature. And the right one is basically dH over dt. And now if we think about only gas-phase reactions, now my dH over dt for ideal gases simply equals to Cp naught. Or the other way to put it is we have the dH naught over dt equals to the change of our Cp naught of the reaction. Or the other way to put it is we have the standard heat capacity of the reaction, and this standard heat capacity of the reaction equals to the sum of each standard molar heat capacity, that's something you can check in the thermodynamic table, times the stoichiometric coefficient, and sum together to give you the standard heat capacity of the reaction. Also, for the standard molar heat capacity, that's something we can express as a function of temperature. This is like not generally true, but what it means is the standard molar heat capacity of a substance is only dependent on temperature. And later on, you have delta H naught equals to T1 to T2 times the change of your heat capacity of the reaction and dt. This part is pretty much just know how to read the thermodynamic table and know what this term, why this term is there. And occasionally in our questions, whenever you're asked to calculate, say, the heat of the reaction, you have, whenever you calculated, say, the heat of reaction of 298 Kelvin, if the question is asking for a heat of reaction at a different temperature, so make sure you want to use that heat capacity of the reaction to translate that heat of reaction for 298 Kelvin into the temperature that you want. All right? Yes. What's that? I'll probably print it out for you, or I'll just give you the number whenever it's relevant. I'm still deciding if how many papers do I want to save, but you'll have it. Okay, and that's all from me today. Do fill out the survey and tell me what to cover for our buffer lecture. That survey is due this Sunday. It's just one multiple choice question. Just tell me which part you're most confused about. All right, I'll see you next Monday.